All right, guys. Today we're going to talk about trying to tie up everything together. What I'm trying to have you guys do, what I'm going to try to do, is help you understand the relationship between quantum numbers, electron configuration, and orbital diagrams. And we're going to talk about orbital diagrams near the end of this lecture. But first, let's talk about what we know, what we talked about the past couple weeks. And now the first thing we have is quantum numbers. And let me change my pen color to, let's see, blue. We got NL, M sub L, and M sub S. Now, N is called the principal quantum number. That's the principal energy level. And then we have L, that's the angular momentum number. Then we have M sub L, which is the magnetic quantum number, or the magnetic moment. We'll abbreviate that. And M sub S is the electron spin. And now we talked about electron configurations. And we have the filling order, which is 1s, and then 2s, 2p, 3s, 3p, 4s, 3d, etc., etc. And now realize that we also discussed that the s orbital can have 2 electrons maximum, p can have 6, and d can have 10 electrons maximum. And this is basically what we talked about last week. Now, I also want to point out is that on these numbers, 1s, 3s, 3d, etc., is that 3 is equal to, when we talk about 3d, we're talking about the third principal energy level and the magnetic momentum number. So the 3d is also equivalent going 3, 2 in the quantum numbers. So when we do electron configurations, we're actually looking at the first 2 quantum numbers. After that, it's going to get a little bit harder to figure out. So let's go ahead and look at the first energy level, and when we look at the first energy level, that's n is equal to 1, and that's supposed to be lowercase n on the screen, but n is equal to 1, 0, and m is equal to 0. There's no ambiguity about this. This is only one way to set those 3 numbers together. So for this energy level, we only got 1 orbital. And we can fit in 2 electrons. And we'll talk about the rules of that in a minute. So we have the 1s, and we can fit 2 electrons in there. And they have to be different spins. And this is the helium. And then if we look at hydrogen, it's just going to be like this. So for the first electron, for any atom or element, the quantum number is going to be 1, 0, 0, 1 half. Always by convention, the first electron in the orbital is always spin up. The second electron in all the elements is 1, 0, 0, negative 1 half. And we have that pointing down. So this is hydrogen, this is helium. Assuming this is helium, and this is hydrogen. I got them backwards. Sorry about that. I was trying to give you guys an idea what this is looking like. So, and this is an orbital diagram. Now, all atoms have the first energy level. All atoms, no matter what. Now, the second, however, only 2 elements have the n equal orbital only, and that's hydrogen and helium. Now, when we talk about ground state, and that's definite, that's defined as the lowest energy level available, or everything low as they can. They're not excited, and there's nothing, no empties above it. The electrons don't have any excess energy. So let's go ahead and look at n equal 2. All the elements have this energy level except for hydrogen and helium. So n is equal to 2, and there's 2 possible L numbers, 0 and 1. So you can have 2, 0 or 2, 1, but that's it. You can't have 2, 2. That's not allowed. L is equal to 0, M sub L, let me put M sub L there, is equal to 0. Then we have two electrons. Or we can just call this positive, and we have 2, 0, 0, negative 1/2. So we have two possible quantum numbers. Now for when L is equal to 1, we're going to have a minus 1, 0, or 1. And you see that these quantum numbers are now getting unique, and these are all positive 1/2. And we also have be negative 1/2. So it's 2, 1, 1, positive 1/2, or 2, 1, 1, negative 1/2. And here's the thing. Now we're seeing where I got the numbers for maximum number 2, maximum number 6, maximum number 10. Maximum number for this orbital, for these three, is going to be 6 electrons. Maximum number we're going to have into the orbital is 2. So when we're looking at energy levels, and for this energy level, we're now splitting the things up. Now, this second energy level, let's go 1s. Here's my second energy level, and now we're going to draw the two p's. And now we're splitting them up into 3 energy levels. This is this is the orbital diagram. And we're going to put electrons in here, 1, 2. Notice how I'm filling, positive and negative, and I'm not pairing up until I get all of them filled. Excuse me. Trying to not to sneeze. Oh, it's winter time, you know, it's that time of year. So this is a set of p orbitals, and only 2 electrons can get in each of these suborbitals. And this is where we come. So if we look at this one, this is the 7th electron. And the quantum number is 2, p, which is 1. Now this is minus 1, 0, 1. So it's actually in the 3rd orbital, third one from the left. So that's 0, and it's pointing up as 1/2. Now I'm going to change the pen color. If I go 0, if I do this 1, 2, 3, this is not correct, because you got to have them split up. You got to move them. They have to fill in sideways and fill up each of these first before pairing. And so that's why I want to point that out to you guys. So every 7th electron, no matter which element you are, they have 7 electrons or more, this 7th electron is going to be 2, 1, 1, 1/2, no matter what. Now we have the 3rd energy level. And so elements 11 and up have the 3rd energy level. L can be either 1, 0, 1, or 2. And depends on what L is for M. This 0 can only be 0, 1 could be these 3, or 2 can be these 3. So here's 2, 6, and 10 for the maximum number of electrons. So what's this look like for the energy orbital diagram? So here's my orbital diagram. All right, 1s, 2s. Now we got the 2p. We always move it up and to the right. So this is the 1st energy level. Here's my 2nd, and the 3rd is 3s, 3p, and the 3d is a little bit higher. And this is my 3rd energy level, my 3d. So this going up is energy. So I'm increasing energy as I going up. And so this, and with this type of chart, with this type of diagram, we only got one axis, and that's energy. And we're just looking at where they are going up. So everything on this line has the same energy. And we're going to put electrons in there. Now the fourth, whoops, typo, this is the fourth. Fourth energy level, n equal 4. And now you know we got possible up to 3 different type of orbitals. S, this is P, this is the D, and now we go to F. We can see that has 14 electrons, total electrons in it. Now what this looks like, and I'm going to show this, is 1s, 2s, 2p, 3s, 3p. Now, here's my 4s, and here's my 3d. The 4s and the 3d are basically almost on the same line. The 4s is actually a little bit higher. Let me rewrite. But the 4s gets filled first because of where it is located. So if we look at that horizontal, here's the nucleus, 1s. 2s, 2p, 3s, 3p. 3d will be here, but the 4s is very close to it. Because the electron cloud is very close to each other, the 4s will get filled first, then the 3d. So it goes from here to here, then down to here. And this is what we mean by 4s always comes first and the 3d, because the difference between these two orbitals are very, very small. Now, how I explain this is that number of orbitals equals the number of protons divided by 2. Oh, you always round up. If the last orbital that we calculate has other degenerate orbitals, always include them all. This is where we get the stability and how we can add electrons to make negative anions. And we talked about this earlier. Now, these rules you need to know. Fill from the bottom, going up, or left to right. This is called the off-bow principle. You need to know this. These are the rules for adding these energy levels. In degenerate orbitals, keep them unpaired first and then pair them up. This is called Hund's rule. Know this. And then by convention, positive spins are first. And each orbital can only have 2 electrons of the opposite spin. This is the Pauli exclusion principle. And so when we draw the energy levels, we can it's very similar to the electron configuration. 1s, again, 2p, 2s, 2p, 3s, 1 line, 3p, 3 lines, 4s is 1, and then the 3d is 5, and then the 4p. Whoops, there we go, 4p. And so this is what it looks like drawing these energy levels, and this is how we do the electron configuration. I am going to stop with this, and we'll do some more examples coming to school on Friday. Thank you, and have a good day.